Okay, welcome to the next lecture. It's the last lecture of the week, so that's always nice. We left off yesterday with, we did Gauss's law, we did electric fields, and we used Gauss's law to find the structure of the electric field. And we were then able to use that to come up with a formula. Finally, after 4 hours of lecture, we were able to come up with a formula for the most basic interaction between two charged particles. That would be Coulomb's law. Now, a little bit of a spoiler is we can use Gauss's law to actually find the formula for the force between any two charged objects, not necessarily point charges. Coulomb's law is specifically only for a point charge, not like an infinite sheet or a parallel plate capacitor or a tube or what have you. Specifically, Coulomb's law is only for a point source. So we will shortly talk about kind of how we're able to use Gauss's law for other scenarios. But before we do that, we did technically cover Coulomb's law. So let's take some time and practice our Coulomb's law. So I think the polling system on Zoom is working now. There was some sort of technical issue in the first lecture. So just to wake us all up, it's 9 in the morning, so I think we're all kind of groggy. Let's do a polling question here. Let me shrink it a little bit, because I think once I launch the poll, your screen is going to be taken up by most of the poll. So here, let's launch this here. There, so you should see something up on your screen now. Hopefully I shrank this enough that you can still read it. So here's the question. If we increase one charge to 4 times Q1, what is the magnitude of F1? So what we do know ahead of time is we know that Q and Q will repel each other because they're the same charge. And presently with Q and Q, we don't know what Q is, but with Q being whatever it is, they repel each other, and F1 feels a force of 3 newtons. So if we increase one of the two Qs to 4Q, what would the new force be? So 14 of you, 15 of you have answered. Of 45, 20 of you have answered, 21 of you have answered. Now, I'm fully aware that I post the slides, which means all you have to do is scroll down to the next slide to get the right answer. However, they're not marked. I mean, I don't know who's voting and who's not voting. And if you are voting, I've got no idea what you're voting for. So being correct in this case is really not the point. It's all about, just trying to get engaged with the lecture material, because it's really a no risk sort of vote. Okay, so just for the sake of time, I think 35 of you have responded out of 45. So I'm going to end the poll, and I'm going to share the results with you. So there's an overwhelming majority of 91% voted C, with a few fringe cases on A and D. I would say most of you got that. So I'm going to stop sharing the results. Very quickly, we're going to scroll down. The answer is in fact C. The reason being is we know force is K Q1 Q2 over R squared. So if we change one, but only one of the charges to 4Q, then this is going to be K times 4Q Q over R squared. And this is going to equal 4 times K Q Q over R squared, which is 4 times the old force. So the old force was known to be 3 newtons. 3 times 4 is 12. So then you get the answer of C. Okay. Let's do another one. So I'm going to relaunch the poll. So you're going to see something pop up on your screen. The question is, same scenario as before. If we increase the one charge to 4Q, what is then the charge that is felt on the other object. We know on the first object that used to be feeling 3 newtons, it now feels 12 newtons. But what about the other object? If I had Jeopardy music, I would probably play Jeopardy music in the background. 13 of you, 15 of you, 18 of you, 21, 23 out of 45, 26, 27, 29. Oh, we're getting there. 33. Oh, I think that's more than what we got last time even. I can't remember. I can't remember 5 seconds ago. 33, 34. Okay, for the interest of time, I think I'm going to stop the poll here. If you haven't voted, that's okay. Like I said before, these are not marked in any way. I don't even know who's voting for what. So it's really a low risk, low reward, or sorry, low risk, medium reward sort of deal. You know, you can be wrong all you want. No one's going to know. So you can always just guess just to let me know that you're here. There's only 35 out of 48 have responded, which tells me there's roughly 13 people that have just walked away from their computer. So I'm going to end the poll, and I'm going to share the results there. So again, we have an overwhelming majority for C. However, we have slightly more fringe cases. We've not as a decisive Democratic vote as we did before, although 66% is still a large majority. So I will say C is still correct, it's still 12 newtons, but for the, let's see here, 30 some odd, 34, 35% of you that did not vote for C, let's take a look as to why. So we know that Newton's third law is always true. And this is what I was saying before at the beginning of the very, very first lecture. This entire class deals with forces at a distance. And gravity, people seem to be fine with gravity for whatever reason. Maybe it's because we can experience gravity on a day-to-day basis. But these sort of electrical forces, magnetic forces, we don't really interact with. I mean, we do, we just don't know that we do. So our brain is not conscious of you know, thinking about the electric force and magnetic force as we are with the gravitational force. But Newton's third law says for every force, there is an equal and opposite reaction force. So if I apply a force from me onto, say, the table, then the table pushes back on me with the same magnitude, obviously the opposite direction. This is still true with the electric force. It's non-contact, so it can maybe throw your brain for a little bit of a loop, but Newton's third law is still there. If you have this charge Q, and it's being repelled by a second charge Q, and they're, well, I guess they're repelling each other, Newton's third law says if the left one is pushing away from the right one, then the right one is equally pushing away from the left one, right? You can't push harder in one direction than the other direction, right? Newton's third law, they're equal and opposite. So we've already established the answer for the previous one was 12 newtons in the event that this is 4Q, in which case the answer on this side also has to be 12 newtons because of Newton's third law. So that's the answer to that one. Okay, so let's speed things up a little bit. I won't launch another poll for this one. We'll just talk about this one. So two balls with charges Q and 4Q are separated by a known distance of 3r. Where should you place the another charged ball of value Q naught on the line between the two charges such that the net force on Q will be equal to 0? Now, we had a question very similar to this previously. The question previously was, does there exist a location in between the two charged objects where the net force would be 0? That was a conceptual question. That was just going with our gut and our intuition. Now, we're actually asked to solve for the location. And we're able to do this now, but not before, because now we actually have a formula for the electric force. So specifically, we need to place a new object, charged object, Q naught, somewhere. I'm just going to draw it here just for the sake of argument. I'm going to draw it here. And if you look at what kind of electric force it will be feeling, we can identify that it'll be a Coulombic force, because it'll be the electric force due to two independent charged particles, not two independent charged plates, not two independent charged sheets, just two independent charged particles. So because of this, because of the particles, we know we can use, I gotta scroll this way, Coulomb's law. So we can draw a free body diagram of this hypothetical Q naught that we're going to be placing. And it doesn't really matter whether we place it to be negative or positive, because they're either both repelling or both pulling, so it's not that big of a deal. If we draw, let's say, assume it's positive without loss of generality, then this will feel, maybe I'm going to try to mimic the colors here. So this will feel a repulsion force from the left-hand side. So this is going to be the force of Q on Q naught. And it's going to feel another repulsive force from the other side, the green one. So this is going to be the force of 4Q on Q naught. So there's my free body diagram. And for it to be in equilibrium, or for the sum of the forces to be zero, then the two have to equal each other. So then that tells us that it's a Coulombic force. So we could say K, Q1, Q naught over R1 squared has to equal K, Q2, Q naught over R2 squared. And you can cancel these. You can cancel the Q naughts. So you see here, Q1 has to equal Q2 over R1 squared over R2 squared. And we know the relationship between the two Qs, right? This is simply just Q R1 squared equals 4Q R2 squared. And now the Qs will cancel. And this gets us R2 squared equals 4R1 squared. Or that's a fancy way of saying R2 equals 2R1. So we know that the distance away from 4Q has to be twice as large as the distance away from Q. So there's practically our answer right there. We have to say, wherever we are, we have to be twice as far away from 4Q as we are from little q. So the whole distance is 3r. Oh, I'm writing black on black, so you won't be able to see that. So our whole distance away is 3r. So we need to divide 3r up in such a way that we're going to get twice as far away from one side as the other side. So that division is going to be r away from q and 2r away from 4q. So the answer to this question will be B. And here's a more elegantly typed solution to that. If you did not like my writing, which is understandable because I'm left-handed writing on a tablet. I've got bad writing at the best of times, let alone on a tablet. So, okay. Just to make sure we're clear, we're going to do a few more of these, and then we're going to do some more rigorous problems. So a proton and an electron are held apart a distance of 1 meter and then released. Which particle will have the larger acceleration at any one moment? So this one I'm actually interested to see what you guys have to say. So I'm going to launch another poll here. Okay, so you should see it pop up on your screens. So again, proton and electron are held a distance of 1 meter apart and then released. Which particle will have a larger acceleration at any one moment? Ooh, 24, 28, 35, 36, 37 of you. 42, oh, we're getting there. much faster. I think people are maybe perhaps more awake now. I don't know. 43. We seem to be plateauing at 43. Okay, it's been about 44. Okay, it's been a few seconds and no one additionally has responded. So I'm going to end the poll and share the results with you. So there we go. Democratically, the answer is B, and that answer won with 59% of the vote. However, C is not far behind with 36% of the vote, and 5% of the vote is A. Now, interestingly, this is why I like to do these questions, because they're simple, they're conceptual, and it gives me an idea kind of where you guys are at, especially now that I can't see your faces and it's not as easy for you to raise your hand. I know Ramina's in the chat, but you know, when we're over a camera, it's a little bit hard to gauge your reaction when material is being presented. So I do like these questions because it gives me a sense of kind of where everyone is at. I'm glad we did this because I just got finished talking about Newton's third law. And although Newton's third law is true, I was sort of leading you down a quasi-trap. I wasn't trying to be malicious or anything, the trap, but reminding you of certain key aspects of dynamics. So the reason why I think many of you, 36% of you, answered C is because I was perhaps just talking about Newton's third law. However, Newton's third law says the force is equal and opposite. That's a very bad handwriting. There we go. The force is equal and opposite. So I agree. If the question had asked which particle feels the larger force, the answer would be C, because of Newton's third law. However, the question asks about the acceleration. And for this, we need Newton's second law, F net equals ma. We know that both particles will feel the same force of attraction because of Newton's third law. However, in order to get a sense of the acceleration, we say the acceleration is going to be the force divided by the particle's mass. Now, between the proton and the electron, they both exhibit the same force. However, they have vastly different masses. The electron is much lighter, so the denominator is much smaller, which means the acceleration of the electron is actually going to be much, much larger than the acceleration of a proton. So the answer is, in fact, B, but not because of Newton's third law being incorrect. Newton's third law deals with forces, not with, oh, I should stop sharing the results so you can get your screen back. There we go. So Newton's third law deals with forces, but not with accelerations directly. For that, you would need Newton's second law. So there's a takeaway there. Okay, so let's go to our first sort of quote unquote rigorous problem. This is not so much rigorous as it is tedious and just a lot of components. I'll spoiler alert that one for you now. But nonetheless, it's good to sort of review kind of basic ideas from 136 and then sort of incorporate them into these new ideas that we have now. So let's read this one. This is example 16 from the typed lecture notes. Figure 18 shows an uneven arrangement of electrons E and protons P on a circular arc of radius r equals 2 centimeters with angles theta 1, theta 2, theta 3, and theta 4. I don't really care what the values are at the moment. The question is, what is the magnitude and direction of the net electric field produced at the center of the arc? So what we have here is we have a distribution of many point charges, not just a single point charge, but many point charges. And we've talked about the superposition of E fields, meaning if you have multiple contributions or multiple sources of an E field, then you can obtain the net E field by superimposing, simply just adding all the E fields together. And you'd have to do this at every single X, Y, Z in the space that you're interested in. So here at the moment, we're only interested in the location at the origin, given the distribution of all the other charges. So we're interested in the E field at the origin. So to do this, I recommend doing kind of what we've always been doing, we know that the electric field is merely a map of the force vectors. So you can think of the electric field as sort of like a force. Had a particle been there, that would be a force, right? That's all E is saying. E is saying if we were to put a particle there, in which direction would it feel that force and with what magnitude? So I know it's not quite a free body diagram because free body diagrams are of force vectors, but E is as close to a force as you can get without it actually being a force. So the way in which you would solve this is simply just by drawing a free body diagram with the electric fields. So here's my Cartesian axis. I am interested in the point at the origin. Now I have an electron. Electrons are blue. So I have an electron here, and in which direction would the electric field at the origin be pointing due to that one electron? Well, we know the electric field due to the electron, yes, is Coulombic, but we know it's radially inward, like this. So that means the electric field at the origin, let me just erase that one there, oops. We know the electric field at the origin due to that electron is going to be pointed to the left. Okay, and we have a proton, protons are red. We have a proton up here at an angle of, what was that, theta 1. Well, protons have an oppositely directed field. It's sort of the same shape, it's spherically symmetric and radially outwards, but instead of pointed inwards, like the electron, it's pointed outwards. So at the origin, it's going to be pointed down over here. Now, what's the angle? Well, we know this angle here is theta 1, so we know this, the opposite angle theorem, this angle is going to be theta 1. That's grade 9 geometry. I remember everyone, when I taught grade 9 math, I remember all my students would say, sir, when are we going to need to know this? And I don't know, maybe in grade 9, it's hard to say how many of them will end up hitting university versus college versus the workforce. So it's hard to answer that question in grade 9, but my answer is usually, you know, if you do pursue higher education at university, guarantee you in almost any science field, you are going to need to know opposite angle theorem in some capacity. Same thing with like C pattern and F pattern and Z pattern and all that other fun stuff. So we are using that here. So there we go, there's theta 1. And we can just keep on motoring. What's my next one? My next one's a proton, so I'm going to keep it red. And protons will point away, so it's going to point down here. This is theta 2 beyond theta 1, so that would mean this angle in here is theta 2. And we keep doing that all the way around. You know, we would do that for the electron's over here, and we would do that for the proton, there's a proton over here. And so we would have multiple contributions, multiple E-field contributions, and what we would do is, we would simply say, we solve for all the X components, dot, 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 and we would solve for all the Y components, and then we would use Pythagorean theorem to put them together. So I don't want to do the whole thing in its entirety, just for purposes of time, but I will start the process for you, just to kind of show you what it looks like. So let's just go systematically. The first object that we had, let me just get rid of some of my needless arrows. The first object that we had was the electron here on the right-hand side. Its electric field contribution is directly horizontal, pointing to the right. So that's in the X direction. So here, I would say this is going to be KQ electron over R squared. Do we have any notion of what R is? R is 2 centimeters. Okay, so I know what that is. R equals 2 centimeters. And Q is, well, Q of the electron is 1.602 times 10 to the minus 19 coulombs. So you can plug, oh, and we know K, sorry, K equals 9 times 10 to the 9. So you can plug in your values later if you'd like. I don't really care to do that presently. Moving along, so the second electric field vector that we added was this one here due to that, sorry, no, it wasn't. It was this one due to this proton here. So this one is partially in the x direction and partially in the y direction. So we're going to need to break it down into components. The x direction component is pointed in the negative x direction, and the y component is pointed in the negative y direction. So instead of saying plus, we would say negative. So this is going to be negative kq of the proton over r of the proton squared. And then we want the x direction. So this is going to be cos theta 1. Now the question is, what is r? Well, r is still 2 centimeters, right? Because all of these charges, whether they be the proton or the electron, they are all placed in a circular arc that has a radius of 2 centimeters away. So this is 2 centimeters. This is going to be 2 centimeters. Everything is 2 centimeters away. So this r value is the same r value as everything else. And we know theta 1. Theta 1 is 30 degrees. Okay, so cos of 30 is √3/2. You can plug that in later, I suppose. Now that's the x component. The y component is kq proton over r squared sine theta 1. And you just keep doing this until you have exhausted all of the contributions. This is what superposition means. You're just adding things together as they come up. The next contribution, I believe, was this guy from this proton here. So again, we're going to see there is a bit of a component in the negative y direction. There's a bit of a component in the negative x direction. So we go through and we say, okay, negative x direction, kq over r squared cos. What's the angle? The angle is going to be theta 1 plus theta 2. So theta 1 plus theta 2, 50 plus 30 is 80. So that would be cos of 80 degrees. And we look, and in the y direction, it's pointed down, so it's a negative y direction. So it's minus kq over r squared sine of theta 1 plus theta 2. Okay, so this is me doing the first 3 contributions. In order to finish this question, you just go through and do the other 2 that I don't want to do just because of time. It's already 9:40. But you know, you just keep going with the same pattern, and you can find the net E field, and then you can find the net. You can find the net E field by doing the Pythagorean. Let me just change back to black. By the Pythagorean sum. So we can say EX squared plus EY squared square rooted. So that's how you can find the magnitude of the net E field. And to find the angle of the net E field, it would be the arctan of EY over EX. So that's a very simple, I guess, application of what we've done in 136, you know, where we do a free body diagram and we look at all the X components, we look at all the Y components, and then we combine the components together. In fact, we started doing that even in kinematics when we were breaking down velocity vectors, and then we continued doing that when we talked about forces as well. Okay, moving right along. Here's another example, using electric force with the prior knowledge of Newton's laws. So this is where you have to sort of tie in some knowledge from 136. An electrically neutral model airplane is flying in a horizontal circle on a 2-meter guideline, which is nearly parallel to the ground. Okay, so that means we have somebody who is flying. Oh boy, this is my really bad attempt at drawing an airplane. Okay, whatever. And then this airplane is traveling in a horizontal circle above my head, parallel to the ground. So that's how you know it's a horizontal circle, because it's parallel to the ground. we know that the line will snap when the kinetic energy of the plane is 60 joules. Okay, so I see a number here, so I'm going to say the maximum, the maximum kinetic energy is 60 joules. Okay, reconsider the same situation of having the plane on a string above your head, swinging around. Reconsider the same situation, except now there is a point charge of positive Q on the airplane. So we have some charge of Q on the airplane, and we have a charge of, say, negative Q on me, the person holding the plane. In this case, the line breaks when the kinetic energy of the airplane is 62 joules. And then we want to find the magnitude of the charges. Now, let's kind of pause and take a moment to kind of figure out what's happening here. When you just swing something at the end of a rope, we already know from 136 that the force responsible for that circular motion is tension. And we also know from 136 that the faster you spin something, the more net force is required to keep it traveling in the uniform circular motion. And the net force in this case is strictly given by tension. So the larger the speed, the more tension is required to keep it in that motion. So when they talk about the maximum kinetic energy of 60 joules, indirectly, they're sort of telling you the maximum speed, right? Because kinetic energy is a function of speed. And if you spun it in, and then the rope will snap, right? You can't, every rope has a maximum load possible before it'll break. Now, why does adding charge help? If you add charge, a positive charge on the plane and a negative charge on our person, then there will be a force of attraction between these two charges. And this means that it will provide an additional force inwards in addition to the tension, and that both of those forces now, the electrical force and the tension force, will be in conjunction responsible for the circular motion. Now, that was me trying to explain the situation. If that went over your head or you're still confused, never fear. Remember my words from 136. If you are asked to do a dynamics problem, like a forces problem, always 100% of the time, start with a free body diagram and then go to F net equals ma. So let's do that. Let's just start with a free body diagram. We have an airplane, and in scenario 1, we have the tension directly inward because it's a horizontal circle. So it's directly inward. I suppose technically we've got gravity, but if it's a horizontal circle, I guess we assume that the wings of the airplane provide the lift to counteract gravity, I suppose is what we're assuming. So this is the free body diagram of the airplane in scenario 1 before the charges are added. After we draw the free body diagram, my advice is to always go to F net equals ma. So what kind of acceleration do we have? Well, F net equals ma, a without any sort of special annotations means linear acceleration. Now this airplane is not traveling in a straight line, the airplane is traveling in circular motion. So we have a special kind of a, it's called AC, the centrifugal acceleration. So then that means we have the net force equals mv squared over r. And the net force is the sum of all of the forces acting on the airplane. So in this case, it's only tension, mv squared over r, there you go. And we see here, what do we have? What do we need? Well, we have the maximum kinetic energy. Kinetic energy is 1/2 mv squared. So I don't have the mass of the airplane, I don't have the speed of the airplane, but luckily I have the kinetic energy of the airplane. So here I can actually see, if I multiply this by 2 times the kinetic energy, I can, divided by R, I can solve for the tension in the string. So note here that 1/2 mv squared equals EK. All I'm doing is I'm bringing up the 2, and I can solve for mv squared all in one fell swoop. So inherently, I've just solved for the maximum tension that this string is able to provide. Now, in scenario 2, oh, what happened? What happened to everything? Oh, come back, come back, come back. There we go. So in scenario 2, we have added a charge on one side and a charge in the center. So not only are we going to have a force of tension pulling in, we're also going to have an electric force pulling in. So now there are 2 forces contributing to the centripetal motion. So there's my free body diagram. We again start with F net equals ma. We know it's centripetal acceleration because we know it's uniform circular motion. And now looking at my free body diagram, I have more than just one force. I have the tension force working together with the electric force, and this is going to equal mv squared over r. And the tension force I know, because this is going to be the maximum, right? The maximum speed, or the maximum kinetic energy, which would be the maximum speed the airplane obtains before the rope breaks. So this is going to be the maximum tension. Well, we know the maximum tension from our previous analysis. So going a little bit further, this is going to be 2 times EK1 over R plus the electric force equals, and again, mv squared, I don't know m, I don't know v squared, but the new kinetic energy in the second scenario is 62 joules. So we can do the same sort of trick. We can swap out mv squared for 2 times the kinetic energy. And I'm kind of losing track what we're solving for. Let's just go back to the question here. Find the magnitude of the charges, okay? So what kind of electric force do we have? Well, we have a singularly charged object. So that's 1 point charge. And we have another point charge at the center of the circular motion. So that's a 2nd point charge. So this is a Coulombic force. So the Coulombic force is given by, let me just rewrite, well, let me just write 60 here just to keep things easy. 60 over R. The Coulombic force is Q over R squared. And this one is 62, I believe, over R. Okay, one of the R's can cancel. R, one of the R's, R. And we are left with 120 plus KQ squared equals 124. And that tells us, oh, sorry, over R. That tells us that Q squared is going to equal R, 4R over K, or Q is going to equal 2 times root R over K. So do we have R? I'm hoping we have R, because we need R. Yes, we do, we have R. R is a 2-meter guideline. So there you go. So you can substitute R here. We're going to get 2 times root 2 over 9 times 10 to the 9. And if you had a calculator, you could plug in your numbers there. Not that I don't really specifically care about the exact value, but that's sort of how you would use themes from 136, how you would engage the prior knowledge from 136 into this new scenario. It's really nothing new, as I mentioned before. We need all the same Newton's laws of motion. It's just now we're adding a new type of non-contact force. You know, we know friction, we know tension, we know normal force, applied force. Well, now we've just added one. We've just added the electric force. Everything else stays the same. Okay, so this is sort of foreshadowing what we're going to be doing next. So I don't want to dwell on this too much because we haven't really talked about electrical energy yet, but we'll read the question anyway to sort of enlighten our minds. So two identical point charges, both of charge 7.2 times 10 to the minus 6 coulombs, are fixed diagonally opposite corners of a square with side length of who cares. A test charge with a certain who cares magnitude with a mass of who cares is released from rest. Yeah.
Someone wants to see the last slide again.
Oh, okay. Let me just scroll. The question or the answer? I'm going to assume the answer.
Sure.
I don't know. Maybe it's the question that they want. I'm not sure.
They said, yep.
Okay. I'm going to assume this is what they want. You can also, if you're watching this on Zoom or something, you can, like live, you can also just take a screenshot of it and then you kind of have a picture of it and then we can move on while you have the screenshot. So that's also a nice sort of feature. Okay, I'm hoping that's enough time. I'm just gonna proceed to go further again. Okay, so where do we leave off? We have a square. We have a square. We have two charges that are fixed diagonally, Q and Q. We have a test charge, Q naught, from one of the empty corners. Q naught from one of the empty corners. Determine the speed of the test charge when it reaches the center of the square. So, oh, and it's negative. And these are positive. So we haven't done energy yet. We will do that very shortly, but I want to motivate the next topic with this question. We're not done with this topic yet. I want to go on to parallel plate capacitors and stuff like that, but I do want to motivate why we need to revisit energy ideas. So here, we want to know how fast it's going to go at when it reaches the center of the square. So first, let's understand why it even reaches the center of the square, first of all, conceptually. So we have a positive charge, we have a negative charge, so we know there's going to be a force of attraction. So I'm going to draw a force this way. And same thing here, there's a positive charge and a negative charge, there's going to be a second force of attraction pulling this way. Well, forces are nothing new to us. We know F net equals ma, free body diagrams. So you can, hopefully you can see that if you pull left and you pull down with the same strength, the net force on this object is going to be a 45-degree angle down and to the left, or southwest, or I know it's not north, south, east, west, but whatever, down and to the left. So the net force is diagonally inward, which means there's going to be an acceleration diagonally inward, which means there's going to be motion diagonally inward, which means eventually the object, this negative Q naught, will eventually pass through the center, which is along the diagonal to the other side. Now, normally what we would do is we would use F net equals ma to come up with the acceleration. And then once we have the acceleration, we would use kinematics to find the final speed, right? That's the sort of story we told in 136. So let's go ahead and try that. We're not going to be able to succeed. I will tell you ahead of time, this method will not work. But let's kind of remind ourselves why this method will not work. So let's go ahead and find, we know the net force is going to be the hypotenuse of this. So each side is K, Q naught over R squared. And the hypotenuse of that means you just multiply by √2. So the net force is going to be √2 K, Q naught over R squared. Is there a side length here? Side length of that. So I'm just going to call it L squared, assuming this square has side length L. So there you go. That's going to be the net force at the starting location here. And the net force is going to equal m times a. So I can actually find the acceleration. Acceleration is going to be root 2 k q q naught over ml squared. Cool. Well, if I have the acceleration, I can then use my kinematics equations and find the final speed. So I can say something like v2 squared equals v1 squared plus 2ad. Do we know the distance this thing travels? Yes. This thing travels half of the diagonal, no problem. Do we know the initial speed of this? Yes. It starts off at rest. So, presumably we could maybe try to solve for the final speed by saying v2 equals the square root of 2a. We know what a is, it's that guy. And then d is half of the hypotenuse. What would the hypotenuse be here? The hypotenuse would be root 2l, and it would be half of the hypotenuse. So you might think to yourself, okay, yeah, no problem, Mark. I can easily solve for the speed at the center. However, the problem is the acceleration is not constant, right? The acceleration is a function of location. Initially, right at the start, but only at the start, is the distance between these two particles L, meaning r squared would be L squared. The moment, the very moment, oh, I just erased my box. The very moment this negative q naught moves forward even a little bit, then this distance is now less than L. And when it moves even closer, let's say even at the target, at the end point, this distance, L prime, is less than L, right? Because this is not 2L, it's root 2L. So the problem here is we do not have a constant acceleration. So you are not able to simply use F net equals ma to find a, and then use kinematics to find final speed, because acceleration is not constant. And if you recall our discussions way back in 136, we were only able to use our kinematics equations assuming acceleration was constant. So why is this important? Why does this motivate the next chapter, which we will move on to later this lecture? Because we've introduced a new force that is a variable force. And if it's a variable force, we are only able to study instantaneous accelerations, meaning we're only able to study the acceleration at one location. It makes studying the trajectory very difficult. And if you recall from 136, the band-aid that we used when we had a variable force was energy. So we will revisit energy later in the class, but I wanted to use this example to sort of motivate why we need to even revisit energy at all. Had the electric force been constant, then there would be no need to revisit energy, and then no physics books would ever talk about it. But because the electric force is a variable, there is a need to talk about it, which is exactly why it's in the curriculum. So everything is here for a reason. It's just trying to make that reason clear is sometimes a challenge. Okay, moving on. Oh, I don't know how it jumped. I don't know how, wow, that jumped really far up. I have no idea how it did that. Okay, here we go. Moving on to the next one. So this one is totally doable. An electron is shot horizontally with an initial speed of, who cares, 5 × 10⁶ meters per second, into a uniform field between the parallel plates shown in the figure below. I know we haven't officially talked about parallel plate capacitors yet, but it doesn't matter because you know, they're telling us it's a uniform field, so that's all that really matters. The field is directed downwards. We have an electron. So notice how the electron is blue and the negative plate is blue and the positive plate is red. This is what I'm saying. I find it hilarious that every textbook I've ever seen color codes electrons to be blue, as if even chemists do that. It's just weird. It's like the one thing we can all agree on is that electrons are blue. Anyway, so what's going to happen here? This is really what I want to sort of illustrate. We have a constant electric field. I don't really care how the electric field is being generated, whether it's in a parallel plate capacitor or an invisible machine behind a curtain, who cares? We have an electron that is exposed to this constant electric field. So we know the electrons will be repelled by these guys and attracted by these guys. So there's going to be a force upward on this electron. And we know in the question that it's a uniform electric field. Uniform electric field means if I'm in a different location, then the magnitude of the field is the same. This is different than the scenario previously. Here, it's not a uniform electric field, because as I moved my negative Q naught in this previous question, I changed the strength of the field. Here, in my new question, if it's a uniform electric field, then E is just constant. It doesn't matter where my X, Y, and Z is. It doesn't matter where I am, it's the same magnitude of E. So if we think back to F equals QE, if E is a constant, then force is a constant. And as soon as we have a constant force, we can go back to using F net equals MA and kinematics when we need to. So that's the premise of this question. So here, what's going on? We have a constant electric field. Oh yeah, and there's a force pointing upwards. So this is interesting because this is exactly what we've studied in 136, but literally upside down. If I throw a football horizontally in the same way that I've thrown an electron horizontally, the football would follow a parabolic trajectory, but downwards, because gravity pulls you down. So the parabola would be downwards. However, this is like gravity pushing you upwards. It's like an upside down projectile motion. It's a constant force, which means a constant acceleration. Constant acceleration means parabolic trajectory. So we're going to get a parabolic trajectory, but instead of down, we're going to get a parabolic trajectory up. So that's the really cool part about this problem. So I'm just going to start it for you guys. So an electron is projected with an initial speed of, cool. So I'm going to write down my givens, because I don't like words. Physicists in general don't like words. So Vx equals 5 times 10 to the 6 meters per second. Into the uniform field between the parallel plates and the figures. The direction of the field is vertically downward. These are all words I don't care about. The field is 0 everywhere except inside the two plates. Who cares? The electron enters the field at a point midway. Aha! Okay, so it enters the field 0.5 centimeters above the plate. Okay. 1 centimeter apart, fine. If the electron just misses the upper plate as it emerges from the field, so that means the electron hits, or I should say doesn't hit, right there. So that means the change in altitude is half a centimeter. Delta D in the y direction equals half a centimeter. Okay. What is the charge density on the plates? Now, if you remember from chemistry or grade 9 science, the symbol of density is usually denoted by the Greek letter rho. So they are mentioning charge density, so I'm going to use rho. Please don't mistake this for the resistivity. I mentioned before when our discussion of conductors and resistors, or conductors and insulators, there was sigma for conductivity and rho for resistivity. There are only so many Greek letters. Eventually, we're going to have to reuse some of them. So this is an example of where we're kind of reusing some of them. Density is usually, so is resistivity. So context, I suppose, is what I'm saying. Context matters. Here, we're not talking about flow of charges, so resistivity does not make sense here in context, but charge density does. So I'm just going to use rho here, so please don't be confused by that. So let's see, where do we go from here? We're not really given a whole lot. We're given the initial speed in the x direction. We're given delta dy, and then we're asked for the charge density on the plates. So we have to sort of link these two ideas. How is the charge density on the plates related? Well, the charge density on the plates are the things responsible for generating the electric field. And the electric field is responsible for the force on the electron. So here, I will trust the analysis, but here I think we should just, when in new situation we're all feeling confused, I think we should just stick to the advice. We have a force, and then we want to know its motion. So let's just draw a free body diagram and go from there. So we draw a free body diagram on the electron. We have the electric force pointed up. Technically, we do have gravity pulling down. However, we know gravity is mg. Well, what's the mass of an electron? Off the top of my head, perhaps, I can't really remember the exact value. I believe it's something along the lines of 9.11 times 10 to the minus 31. Think about that. This is of the order of magnitude 10 to the minus 31, 31 decimal places. And sure, G is times 10 to the 1, like 9.8. So mg is going to be of the magnitude 30 decimal places. It's going to be ridiculously small. So we actually just sort of approximate this to 0 most of the time, because it's so small that, you know, the electric force might be 6 decimal places. Well, 6 decimal places might seem small, but it is actually vastly larger than 31 decimal places. So it's actually 10 to the 24 times larger than the gravitational force. So you're correct. If you want to label the gravity here, no TA will mark you wrong. You're just doing more work than you have to. You can ignore gravity and still get full points. So we got the electric force pointing up. So we go to F net equals ma. So we say the acceleration is going to be the net force, which is Fe over the mass of the electron. And we know it's a constant electric field. So this is just simply going to be QE over mass of the electron. So we're getting somewhere. We now have the acceleration as a function of Q, which we know Q, because it's an electron. I suppose I forgot to write that down. 1.602 times 10 to the minus 19 coulombs. We know the mass of an electron. I believe, don't quote me on this, but I think it's 9.11 times 10 to the minus 31 kilograms. So really the only thing here we don't know is E, but that's okay. We're getting closer and closer to what we want, sigma. Let's see if we can sort of encompass other things. Because we haven't used Vx yet, we haven't used delta dy yet. We would normally go to our kinematics equations, and we notice that the acceleration is constant. Q is constant, m is constant, E is constant. So we can absolutely go to our kinematics equations. So what kinematics equation do we have that has delta dy in it and the acceleration? With some thinking, you'll figure out, hopefully, it's delta dy equals v1yt plus 1/2 a t squared. Well, the initial speed in the y direction is 0. Delta dy, we know, so check mark. Acceleration, we know, check mark. Time, well, we don't know time. Do we really need to know time? I don't know. Another equation we could possibly use is v2 squared equals v1 squared plus 2a delta equals 2ay dy. Well, we either solve for time or All right, I think I'm back. I think I'm back. Am I still recording? Yes, all right. I think I'm still recording. All right, that was weird. I don't know what happened there. Technical problems all around, I suppose. Okay, so we have two options. I'm not sure exactly where I was cut off. We have two options. We can use this kinematics equation, or we can use this kinematics equation. So the question then is, from a student perspective anyway, the question is, which one is more useful to me? Which one should I use? We notice here that both of these equations use delta dy. Which piece of information have we not used yet? We have not used the speed in the x direction. We have not used that yet. So how can we use the speed in the x direction? Which equation, 1 or 2, will make us better able to use v in the x direction? And a common theme you might recall from 136 is you often couple the x direction with the y direction using time, because the time is what's common between the x and the y. You spend the same amount of time traveling in the y direction as you do spending the time in the x direction. So because of this previously established trick or analysis method, I'm leaning toward using the first option. So we also know delta dy equals 1/2 a t squared, which means t is going to be equal to the square root of 2 delta dy over a. And luckily we know a. What was a? A was QE over m. So this is going to be 2m delta dy over QE. There you go. So there's your time. And from here, in the x direction, I say Vx equals dx over time. And there's where you can introduce your v in the x direction. So I would say we have Vx equals dx. Dx is 2 centimeters, so we have that. Over time, oh, well, I don't want to, I'll just multiply by the inverse. 2m delta dy. And there you go. So let's see here. What do we have? We have Vx, we have dx, we have q, we have m, we have dy. The only thing we do not have in this equation is the electric field. So I want you to just metacognition for a second. I want you to reflect on what we've done. We entered this question not fully understanding how to link what we're asked for and where we're starting, right? We entered into this sort of blindly. And I want to sort of demonstrate to you that that's okay. Okay, with especially physics in an academic setting, like in school, problems are usually very well defined. And you can often solve many new problems you've never seen before simply by just sticking to the advice that was told to you. Starting with basics, starting with things that you know, and just following the math, you know? That's what we've done here in this solution. And even presently, I have not yet presently identified how to link rho, how to solve for the charge density. That's okay. Look how far we've gotten not knowing what to do. You know, we stick to basics, drew a free body diagram, did F net equals MA, used our prior knowledge from 136 to move from F net equals MA into kinematics. Look how far we've gotten. If you were on a test and you did all this, this would be like an 8 or an 8.5 out of 10. And that's a pretty good mark for not knowing immediately what to do, right? You just stick to basics and implement that. So that's what I want to illustrate to you here is reflect on this, Moving right along though, you could solve for E. So what's E? E is going to be, let's see here, square everything. So Vx squared times 2m delta dy over dx squared equals QE. which means E is going to be 2Vx squared, mass of the electron, delta dy over Q d dx squared. All right, so we now have a formula for the electric field. Now, if we knew how to relate the electric field to the charge on the plates of a parallel plate capacitor, we're golden. So here, all we need is the relationship between, that's not a B, between E and charge on plates. Oops, that's plates. So that is something we're missing, right? We have the E field. Conceptually, we understand, look, this is a constant, right? 2 is a constant, the speed in the x direction is a constant, the mass of the electron is a constant, the distance traveling in the y direction, 0.5 centimeter, is a constant, Q is a constant, and 2 centimeters in the x direction is a constant, which means the E field is a constant. Now, I grant you there is one piece of this puzzle we are missing, and yes, it is the linkage between E and the charge on the plates. So if we had that, we could solve this question. Done. Please understand, even if you don't have that piece of information, we were able to do 90% of the problem just by using basic knowledge. So this is an exercise of problem solving skills. Now, I'm going to use this to motivate. I don't know why it does that. At the bottom of the screen, it always goes wiggly. I'm not sure why. Okay, I'm going to use this to motivate a new setup. I'm showing you that there's a piece of the puzzle in our story that's missing. So now let's pause and go look at that missing puzzle piece. It's the parallel plate capacitor. So I told you our whole goal as a scientist is to notice a phenomenon and then explain it. We've noticed the electric force and we have explained it. The way in which we come up with a formula for the electric force is Gauss's law, draw a Gaussian surface, use Gauss's law to find E, and then use F equals QE to find F. I can write that down here. First we use Gauss's law does not start with an F. Use Gauss's law, find E. Then we use F equals QE to find F. Okay, that's the general method by which we solve for F. Now, we've done this once before with Coulomb's law, KQQ over R squared. However, I could not have stressed this enough yesterday. That is one very, 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 very specific scenario between two charged particles. We do not have two charged particles. In our situation here, we have one charged plate and a second charged plate. Those are not 2 point sources. Those are two oblong-shaped objects. So we can't just assume the force between those two plates is KQQ over R squared, because that does not fit the assumptions of that derivation. So, new scenario, we go back to the starting equation, because that's what starting equations are for. That's what we use F net equals ma for. F net equals ma is a very well-known starting equation. And F net equals ma produces all sorts of different answers. It depends on your situation. So let's do that now with Gauss's law. So, new situation. Gauss's law, if you recall, Gauss's law says the integral of E dot dA equals Q total over epsilon naught. And in our class, we are trying to make three assumptions. One, we need to pick a Gaussian surface such that, one, the E field is constant everywhere along the Gaussian surface. Two, the second assumption we needed to make was that the angle was constant everywhere along the Gaussian surface. And the third assumption we need is that we actually know the formula for the area. If we can find a Gaussian surface that satisfies these three things, then Gauss's law simplifies to EA. Oh my God, it's going all wiggly again. Come on. Okay. If we can find something that satisfies this, it's going to be EA cos theta equals Q total over epsilon naught. Okay. So we have a parallel plate capacitor. Let's see if we can find, well, actually, I don't want to look at that drawing. I want to start from scratch. We have a parallel plate capacitor. We've got one plate is known to have positive charges, and we have the other plate is known to have negative charges. Before we use Gauss's law, we need to have some notion of what the electric field looks like, because we need to make sure that the E field everywhere along our surface is constant. The only way to do that is to have some sort of idea ahead of time of what the E field looks like. And same thing with angle and same thing with area. So let's see if we can use some logic and problem solving skills to sort of come up with what the structure of the E field might look like. We know that each of these charges, when you zoom in, zoom in, zoom in, zoom in with a microscope, will be emitting their own Coulombic E field. However, if you look at that, now you get the idea with all my vector drawings there. You know they're going to be emitting many radially. Now let's look at something here. One of them is going to be pointing down this way, and next to it, you're going to have, again, pointing in all directions. One of them next to it is going to be pointing this way. Well, that means you're going to get cancellation. That means the horizontal components will cancel, and the only thing that survives are the vertical components. And that only happens because of the compactness and how close together all of the charges are. If they were farther away, then they would be individual charges like Coulombic. But because they're packed really, really, really close together, all of the horizontal components will cancel out, and only the, all of the vertical components will cancel out, and only the horizontal components are left. So inside, what's going to happen inside is you're going to get the E field. Oh, sorry, there we go. They're all supposed to be the same length of vector. Inside, all the E fields are going to be pointing horizontally. Now, on the outside, the same thing is going to happen. On the outside, they're all going to be pointing horizontally. And if you remember the E field of a parallel plate capacitor, don't be yelling at me right now, because I know we're not quite done yet. On the other side, same thing. They're all going to be pointed inward radially, but all of the vertical, all of the up-down components are going to be canceling because of the proximity of the neighboring negative charges, that the only thing that's going to survive are the horizontal components. And then these are going to be pointing like this. Now, one thing we're forgetting. Electric fields can pass through conductors. It's true that inside the conductor, the electric field is zero, but beyond the conductor, the E field can go right through it. So this electric field here pointing to the right actually extends and also points this way. And same thing on the other side. On the other side, this electric field extends beyond the plate and points backwards. So there's the sort of destructive interference beyond the plates. There's a constructive interference inside the plates, right? Inside the plates, they're in the same direction. But outside the plates, they're in opposite directions. The question is, do they perfectly cancel out? Because if you think about it, these electric fields are really close to the positive charges, so presumably they're really strong. And the negative, the black arrows are farther away from the negative charges, farther away from their own source. So presumably they're weaker than the red arrows. Now, in order to rectify this sort of uncertainty, we can actually simply use Gauss's law. If we take a Gaussian surface and we encompass the entire parallel plate capacitor, then we see Gauss's law says the E field is proportional to the total enclosed charge. What's the total enclosed charge if we enclose the entire parallel plate capacitor? Well, we have a charge of positive Q on one plate and a charge of negative Q on the other plate. So the total charge is positive Q plus negative Q. So overall, EA is going to equal 0 over epsilon naught, which means E is going to equal 0 over A epsilon naught, which just equals 0. So Gauss's law predicts that on the outside, when you encompass the entire parallel plate capacitor, that these in fact perfectly cancel. And the only field that exists is inside, which is kind of it's like a nested application of Gauss's law. It's really cool. So after some preliminary work, we can deduce that the electric field inside a parallel plate capacitor visually looks like what is here in the slide. What we do not know is the equation. We do not know, is it a constant E field inside here? You know, presumably, intuitively, it makes sense to think that a location that is really close to the positive plate would feel a stronger force, i.e. having a stronger electric field. And similarly, a location close to the negative plate would be close to the negative plate, so it would be stronger. And then, you know, you might think that somewhere along the middle is the weakest, because it's a maximum distance away from any of the two plates. We don't know. That's kind of what we're here to find out. Now, this is where you need to really plan hard the parallel of the Gaussian surface, because whatever surface you choose, we don't know the E field. So whatever surface you choose, every location along the surface must have the same strength of electric field. The unknown strength of the electric field, but we should be able to predict and ensure that it's constant everywhere. So what we're doing here is we have our sort of plates. Okay, and we know we have an electric field inside the plates. What we do is we pick a Gaussian surface. I'm going to choose green for my Gaussian surface. We choose a Gaussian surface to be rectangular. It's a rectangular slice of part of one of the sheets. So this here is my Gaussian surface. And you can see the sort of cross-section Gaussian surface here in this diagram. All right. In three-dimensional space, this is a rectangular prism, is my Gaussian surface. So Gauss's law says the flux equals the total enclosed charge over epsilon naught. We know what the flux is. The flux is how many electric field lines, the number of E field lines that pass through the surface. So we have 6 sides of this prism. So we're going to do the flux for side, well, the flux for the left side, the flux for the right side, oops, plus the flux for the top, plus the flux for the bottom, plus the flux for the front, plus the flux for the back, equals Q total over epsilon naught. So let's go ahead and do this. Let's say the left-hand side. The left-hand side is over here. How many electric field lines are passing through the left-hand side? Now, if you don't really fully understand my 3D drawing, let's go look at this slide here. How many electric field lines are passing through the left-hand side? None, right? This is why it's important to have thought about the electric field structure in advance. So there are no electric field lines that pass through the left-hand side. How about the top? How about the top of my box? Well, the top of my box is here. How many electric field lines are passing through the top? I agree there are some field lines that are passing over the top. You know, there's an electric field line that passes over the top like this. But how many electric field lines will pass through, not over, but through the top? And the answer is still 0. And the bottom. How many field lines are passing through the bottom? Again, there are no electric field lines that are passing through the bottom. And how about the front of the box, staring at me in the face? Well, again, if we scroll up here, how many electric field lines are coming? All of the electric field lines are traveling to the right. So how many are traveling out at you? 0. And how many are traveling into the board? 0. So the only one that survives is this one. How many field lines are passing to the right? There are EA of them, right? Because remember, flux is EA cos theta. Theta in this case is 0, cos of 0 is 1. So how many field lines are traveling through the right side? There are E times A. So this whole surface here is A. And there are E times A field lines traveling through that surface. Now the question is, what is A? A is the arbitrary area of my Gaussian surface. I could have chosen to draw a small rectangular prism. You could have chosen to draw a large rectangular prism. Okay? However, although the area you draw will change the value of A, it also changes the value of E. If you draw a small area, then you have a smaller amount of electric field that goes through it. If you draw a larger area, you have more electric field that goes through it. So they will grow and shrink in proportion to one another, which means their product will be the same. Now, the way to get around this is we can assume this is just simply the area of the entire plate. And then this would be the E field generated by the entire plate, not the E field generated by half the plate, not the E field generated by a quarter of the plate, but the E field generated by the entire plate. And this is going to equal the total charge on the plate divided by epsilon naught. So here we see that the electric field inside a parallel plate capacitor is going to be the charge on the plate divided by the area of the plate times epsilon naught. And there is your electric field inside a parallel plate capacitor. Notice something. E is a constant. It's a constant because it's not a function of location. It's a function of the charge on the plate, that's a constant. It's a function of the area of the plate, that's a constant. And it's a function of epsilon of the epsilon of free space, that's a constant. So this is a constant value. We had the same starting equation as before. We had Gauss's law. We used Gauss's law to come up with Coulomb's law. Oops. Coulomb's law, or I guess Coulombic E field, was KQ over R squared. The R squared came in from the fact that our surface area was 4 pi R squared. And the larger you decided to draw your Gaussian sphere, the larger the R was, meaning the farther away you got, the weaker the Gaussian, the weaker the E field. Here, the area of the plate, it doesn't matter whether I choose to make this side length longer. This area here was simply the area of the right-hand face. So the width of my Gaussian surface drops out. It doesn't become a function of my answer. The only variable in my answer is the right side face of my Gaussian surface. And that's just simply the area of the plate. It's not a function of how deep the Gaussian surface is. So this is what I'm saying. It's very bad for textbooks to say, oh, here's the electric force, it's Coulomb's law KQQ over R squared. Because that tells students for the rest of the class, the electric force is always KQQ over R squared. And it's not. Sometimes it's KQQ over R squared, sometimes it's constant. It depends on your situation. So this is the new equation. And this is the piece of the puzzle that we were missing for the previous question. How is the E field in a parallel plate capacitor related to the charge? Related to epsilon naught. How does that solve the problem? If we scroll up back to, where are we here? We have the E field. We have the E field. So we know E is going to equal to Q over A epsilon naught. And they're asked for, or we are asked for, the charge density in coulombs per meter squared. We are asked for the charge density in coulombs per meter squared. So this is going to be rho over epsilon naught. So if we have E, all we need to do is say the charge density is sigma epsilon naught times E. And then we have the charge density. So this is what I was saying before. Even though we had a piece of the puzzle missing when we tried to attempt this problem, sticking to basics, doing a free body diagram, doing F net equals ma, using kinematics, and using our very basic knowledge of F equals QE, we were able to obtain 95% of the answer. The only thing we were missing was this one equation. So you could actually, my point is, on a test, even if there are details you forget, you can probably achieve many of the partial marks just by sticking to basics. Okay, that is the end of the first part. It's not quite the end of electrostatics, but it's the end of sort of Gauss's law and the electric force. So I'm going to pause the video here, and I'm going to make a new video because we're going to be starting a new chapter. It'll specifically electrical energy. So if you're watching this on YouTube, I will see you in the next video.